Hello and welcome again to my Physical Science Online Video Lecture Supplement series. Today's video is another of those post-quiz review videos, and this one is for the lecture quiz number 3, which was the quiz that covers the chapter on forces and motion. So let's have a look at the item analysis. Alright, so this is the Quiz 3 item analysis, force and motion, and it looks like people did a little bit better on this one again than on Quiz 2. So here's hoping that Quiz 2 was just a low water mark and not a pattern of doing well and then doing poorly and then doing well and then doing poorly. For what it's worth, on the first quiz the average score was an 88, for the second it was a 63, and now we're back to an 80, so we're back in the high B range as an average. So good work, guys. Looking at the questions, we want to actually organize them in order of difficulty. And again, there's certain questions that only some people got and some people did not. So let's look at the ones that everybody actually had. And I should add here, because I see that the very first question that a lot of people missed was marked EXE 12A modified. I want to add as a point of reference for these quizzes that when I pull something from the textbook, I have some code usually, like EXE means an even numbered exercise, and usually I just use the actual numbers in the hard copy book, but sometimes I modify it slightly, and I try to remember to put in a little note that it's modified, or maybe I'll write MOD for modified. This one, the modification in there was in the units. It looked like it threw a few people off a little bit, so it's a good idea in general to read the question carefully and be sure that it really is the same question that you worked on your homework. This is especially true given that many of you are using WebAssign, so the numbers are going to be different anyway. So with that aside, it looks like this is the most frequently missed of the questions that everybody attempted. Looks like there's also a few questions that a fair number of you attempted and did not do so well on. So what I think I'll do is I'll go ahead and look at these two questions. I'll look at this question, and really the only other one that is of significant interest here might be this question. This is a modified example. All right, so the first question that a lot of people missed, and in fact that everybody who attempted it, the quarter of the class that attempted it, missed, is this multiple choice, multiple answer question that I wrote, which is basically says the force of gravity between any two objects is which of these following. So let's look at our options. Option 1 says it's larger for the larger object than for the smaller object if the two objects are not the same mass. We can in fact eliminate this option, and the reason why we can eliminate it is because, and let's actually pull open the textbook in order to see this whole answer. It is because of Newton's third law of motion. So let's go to the section on Newton's third law of motion. And again, let's maybe zoom in so we can actually read what it says. So Newton's third law of motion is the one that is sometimes the action-reaction. It says the action force is equal to the opposite of the reaction force. F1 equals negative F2. Where F1 is the force exerted on object 1 by object 2, and F2 is the force exerted on object 2 by object 1. So what does this have to do with Newton's universal law for gravitation? Well, we've written here that the force of gravity between two objects is it larger for one object or for the other object? Well, this force of gravity exists between two objects. So the force of gravity that object 1 applies to object 2 is going to be the action force, and the reaction force to that is the force of gravity that object 2 applies back on object 1. So by Newton's third law, these two forces should be equal, and that's true regardless of whether the two objects have different masses or not. So what is actually going to be different between the two objects? Well, the force is going to be the same on both objects, but the acceleration of the two objects is going to be different. The larger object will have a smaller acceleration. The smaller object will have a larger acceleration. The smaller object is going to, if they are initially at rest, is going to look like it moves a lot more than the bigger object is. So this one's out. Okay, our second option says that the force of gravity between two objects gets weaker as the two objects get closer together. So let's go ahead and look at Newton's law of gravitation. And in fact, what we want is this equation right here. Force equals G m1 m2 over r squared. So gets closer together. What does that have to do with this equation? Well, the r in this equation is the distance between the two objects. So if the two objects are getting closer together, r is getting smaller. And you can see if r gets smaller, then f is going to get bigger. And that's all I want to say in this video about that one, other than that if you don't see that, what you can attempt doing is you have a value for G, you have a value for M1, you have a value for M2, or you can assign values to M1 and M2. Let's say that we assign values to M1 and M2 so that G M1 M2 has a total magnitude of, let's say, 1 Newton per meter squared. 1 Newton times meter squared. Alright, so what would happen then if we started plugging in values for R? Alright, so let's say that we will put one column that is for the value of R in meters, and the other column can be the value of force in newtons. Okay, we're not going to do 0 meters because we don't want a 0 in the denominator, but let's try 1, let's try 2, and let's try, say, 10. So that gives us 3 different values that we can use. And what you basically do is you say, okay, for 1 meter, we have 1 divided by 1 squared. So this right here, this equation right here, we could actually write as 1.0 Newton meters squared divided by whatever R is squared. Alright, so this one maybe you don't need the calculator for. We would have 1 divided by 1 squared. So that, of course, is 1. Okay, for the second one, we would have 1 divided by 2 squared. So 1.0 Newton meters squared divided by 2.0 meters squared. Okay, so here's how you do that on the calculator. On my calculator, you put in a 1, you say divided by 2, and then you square the 2. And we get 0.25. So this is going to be 0.25 newtons. And in fact, I have the unit up here, so I don't really need to write it in here if we don't want to. This one right here, we're going to end up with 1.0 Newton meters squared divided by 10.0 meters squared. 10.0 meters squared is 100 square meters. So 1 divided by 100 is 0.01. Okay. So notice that as R is getting bigger, F is getting smaller. The opposite way of saying that, the conversely true statement, is that as R is getting smaller, F is getting bigger. F is getting bigger is the same thing as saying that the force is getting stronger. So that's the opposite of what this option says. Alright, next option nobody picked, so I'm not going to review it. Good for you guys for knowing that this one's wrong. Next option says that the force of gravity between any two objects is g equals 9.81 meters per second squared. This quantity, g equals 9.81 meters per second squared, is what's called the free fall acceleration. It's the acceleration due to gravity which an object near the Earth's surface will experience. So notice that there's a lot of qualifying terms that goes with that. For one thing, it's an acceleration. This is asking about a force, so we can eliminate it just on that. We could also eliminate it, even if there was some confusion between those two things, by noting that this is the specific acceleration due to gravity that an object near the Earth's surface has. That's not the same thing as the force of gravity between any two objects. So we can eliminate this option. This one says that it depends more strongly on the larger object's mass than on the smaller object's mass. It actually depends on both of them the same. And again, to get that, you go to that equation, which says that F equals g m1 m2 over r squared. Both of these terms are to the first power. They're both multiplied by each other. That means that this total force is going to depend equally strongly on both of these. It would be more strongly dependent on one or the other if it said, for example, force equals some constant times the bigger mass squared times the smaller mass over r squared. Okay, in that case it would depend more strongly on the bigger mass. Or if it said g times smaller mass squared times bigger mass divided by r squared, then it would depend more strongly on the smaller mass. But it doesn't say that. It says g mass over r squared, big mass, little mass. So it depends on both equally. Okay, that leaves us with this as our last option. This one says force of gravity between two objects depends on the density of the object, so that if density increases but mass remains the same, the force of gravity will increase. I guess maybe two people must have picked this if I'm reading this correctly. And actually this one is also false. If you look back at that equation again, the dependence is on the mass of the objects, not on the density, and it says mass remains the same. So if mass is remaining the same and density is increasing, then there should be no difference in the force. So we've actually at this point eliminated all of the possible options. So that means that the answer must be none of the above. And you see the check mark here means that's the answer. Okay, the next problem on the quiz that I wanted to look at is one of the calculated numeric questions. It was basically even numbered exercise 12A in your book, and of course it's modified slightly. Modified again means I modified it from what the hard copy of the book has, which is also the electronic copy of the book, but not what WebAssign has. And the modification that is involved is right here. In the book, it's 25.0 meters. In this particular quiz question, it's 25 kilometers. So what does that do? Well, we're going to actually use the same equation that I showed earlier for force of gravity, which is that the force of gravity is g m1 m2 over r squared. Now, the problem actually gives us all of these three terms, and this one, of course, is a universal constant. So for big G, you can look it up in your book or in your notes. Here it is in your book, for example. G is the universal gravitation constant and has a value of G equals 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So we've got the value of G. The masses M1 and M2 are the masses of the two cars. So that's given right here. They're both 1,000.0 kilograms. And of course, the r squared term represents the distance between the two cars. So that's given right here. They're separated by a distance of 25.0 kilometers. Okay, so we have all the numbers we need. Let's go back to our equations. So here is the equation we're using. Here are the terms that go in that equation. Whoops, this should say 25 kilometers, not 25 kilograms. And the key thing here is that 25.0 kilometers is the same thing as 25,000 meters. Reason why we need that is because if you look up here at this term right here for G, it's in Newton meters squared per kilogram squared. So we have to convert from kilometers to meters to make these units and these units agree. Kilograms are okay, we're going to get the force in newtons. So this equation therefore becomes 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times mass of car number 1, which is 1,000.0 kilograms. So I guess that's more like this, times another 1,000.0 kilograms. And all of that is going to be divided by this distance squared. So we have 25,000 meters, and we're going to square that distance. So on comes the calculator. 6.67 times 10 to the minus 11 basically gets entered like this. We go power, we go that power needs to be negative, then we say that it's 10 to that power. It's kind of a funny way of having to enter a number. Okay, now we multiply that by the first 1,000. So that's this term. And we multiply that by the next 1,000. So that's this term. And then we're going to divide that by 25,000 squared, which is this. So what we get is 1.0672 times this power of 10. So what power of 10 is it? Well, you can count. So 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's 1.0672 times 10 to the minus 13. So this means that the force is, if we round that, it becomes 1.07 times 10 to the minus 13 newtons. So that's the answer we're looking for. Now, of course, you have to actually put this in scientific notation. So you'd enter this as 1.07 E13, or if you want, you can put E plus 13. And that's just how you enter it in scientific notation so that it's entered into the question. Into the answer space for the question. And you see here it's 1.07 E minus 13. I put a plus, I meant a minus. So actually it should be E minus 13. Alright, last but not least, we have to do this question that half of you got right, the other half got wrong. And it looks like this. So you have a child's cubic block. It's given some mass, it's got sides with some length, it's placed in a bathtub full of water, and we want to know what is the fraction that's going to be submerged. So the relevant section of your book for this is 3.6, which is Archimedes' principle and buoyancy. So you can review that section if you'd like. Some interesting facts here. If you have a density that's less than the density of the fluid, it's going to float. If it's greater, it's going to sink. If it's equal, then it has neutral buoyancy, and so it'll just stick at whatever level you happen to put it at under the water or under whatever fluid you're using. The most relevant equation, though, to use for this is found here in our notes, and this one says that the volume of the fluid displaced is going to be equal to the volume submerged of the object, and that is the density of the object divided by the density of the fluid times the volume of the object. And in fact, I worked a similar example. It does say that it's MEX 13. That basically means that it's a modified version of this example here. So what that looks like is this. Basically, the thing that we're looking for is V sub, and we're given that V sub is density of the object divided by density of the fluid times the volume of the object. And recall that the actual thing that we're looking for, what we want, is the fraction of the object which is submerged, which is basically this ratio right here. This would be, we'll just call it fraction of object which is submerged. And so that is the total volume of the object. So V is volume which is submerged. So this right here is going to depend not only on how much the object floats or sinks, in other words, on what the ratio of density is, but also on the total volume of the object. In other words, suppose that you have a pebble and you have a boat. Well, the boat is presumably floating on the water, and if you drop the pebble into the water, it's presumably going to sink. But if you just look at how much volume of each object is under the water, the boat has a much larger volume that's underwater than the pebble does. Why is that? Well, because the boat is a lot bigger. So that's where this volume of object comes into play. VOBJ is basically what we would call total volume of the object. And so the bigger the object is, the more total volume of that object could be submerged. Okay, and this ratio, rho object over rho fluid displaced, or rho fluid, is basically just a description of how floaty is the object. So rho object is density of the object. And recall that this is equal to the mass of the object divided by the volume. So this is mass over volume for the object. Okay, and last but not least, rho FD is density of the fluid. And the fluid in this case is bath water. So you can look up what the density of water is. It is basically 1.00 grams per cubic centimeter. Okay, so that number is given. All right, so basically what we have to do is, to get our answer, we have to compute what the value of this guy is. And since we're dividing by this guy, we're really just dividing by 1. So, and then the additional rule is that if the object actually sinks, then the answer has to be 1. Because you can't have, an object that has a volume of, let's say, 30 cubic centimeters cannot have 60 cubic centimeters underwater. The maximum volume underwater would be 30 cubic centimeters. Okay, so what we need to do here is actually compute what the volume of the object is, because we're given the mass of the object in the problem. So going back to that problem again, here's the mass. It's 120 grams. So that's given, and it's a cubic block with sides of length 5.0 centimeters. Alright, so basically the object itself, if you'll pardon my poor drawing skills, is going to look something like this. And basically each side is given as 5.00 centimeters. So how do you get the volume of a block? Well, the volume V, we'll call it volume of a block, is length times width times height. And so each of these things is 5.00 centimeters. So this total volume must be whatever 5 times 5 times 5 is. Well, 5 times 5 is 25. If you multiply that by another 5, you get 125. If you don't believe me, you can plug it into a calculator and double check. So volume in this case is equal to 125 cubic centimeters, because you have centimeters times centimeters times centimeters. Alright, so if we put all this together, what we end up with is this. V submerged over V object is equal to rho object over rho fluid. So that's going to be mass over volume for the object. I'm going to abbreviate it as an M for mass and a V for volume, divided by the density of the fluid. So that looks to me like what we have is 120 grams divided by 125 cubic centimeters, and then all of that is divided by 1.00 grams per cubic centimeter. So this one we've pulled from here because it's water. This one was given in the problem. This one we just computed above. If you put all this stuff into your calculator, what are you going to get? Well, you have basically 120 divided by 125, and that's 0.96. And divided by another 1 is still 0.96. It's just that we were able to eliminate the units, which is what we want to do. So the answer here is 0.96. So that's all that I wanted to cover in this particular post-quiz review. Looks like you guys did better this time around than last week's, so I hope you're all able to keep that up, and I hope that you find this post-quiz analysis helpful. In any case, thanks for watching, and good luck next time.